I'm Joe Anderson with the Fish Project at the University of New Orleans, REU, and we're going to present to you our project which was on fish detection and classification in underwater video. And with me are Colin O'Byrne and Brian Lewis. So first, I'll start, give you a brief introduction, our goal for the project and the first steps we took. Then I'll go into some background subtraction methods that we used and automatic thresholding. Then Brian will talk about feature extraction using warp and Gabor filters, and Colin will discuss the classification system, and then we have some conclusions and possibility for future work. So for the project, our goal, as kind of implied, is to use footage taken of fish swimming and identify them by species. And to do that, we implemented several core components to the project. Background subtraction to find what was not originally in the frame. Automatic thresholding to segment out blobs or objects of the foreground. Image segmentation and warp and Gabor filters to extract features. And classification networks to actually give us an answer as to what kind of fish is this. So background subtraction is used to calculate from a sequence of images a common background. And the method we used a running mean. So it took a sequence of about 115 images and took the mean value of the pixel for that sequence, and it would generate a background like this. This is what we actually calculated for our series. And then it would actually subtract that background using matrix subtraction from each frame, and you get something like this. And then from this point, this is where we would use automatic thresholding methods to segment it and decide what's noise. Like there are some parts that we can kind of intuit that aren't part of the fish. So we would use methods to find what's fish and what's not. So the background, some of the automatic thresholding methods we used were class variance methods. One in particular was Otsu's method, which models the image histogram as a probability function. Using the histogram as a probability function, it will separate the pixels into two classes, above and below a particular threshold, calculate the variance of the two classes, and try to maximize the difference of the variances. The next method we tried was a clustering method, which would again use the histogram, but try to fit it against two Gaussian mixtures. And this method assumes that the objects we're looking for, foreground and background, are distinct. Only two levels, not like foreground, middle ground, background. So it would take two Gaussians and try to fit it to the histogram. And using that, trying to solve that fitting problem, it would try to minimize an error and therefore obtain a good threshold. Another style of thresholding algorithm uses entropy. Xiao's method in particular uses a two-dimensional gray level spatial correlation histogram. And this is a standard histogram, but also it calculates the number of similar neighbors in addition to pixel intensity. So instead of the probability only that a pixel will be a particular intensity, you'll get a histogram representing the probability that a pixel will be a particular intensity and have a given number of similar neighbors. The next entropy-based method was by Ajlan, and he uses a cross-entropy method on the gamma distribution. And the novelness of this technique is that the gamma distribution can handle asymmetrical histograms, not only histograms that peak and then decline at the same rate. It could have a sharp peak and then abnormal on the other side. And another style uses the graph cut technique, which will model an image as a graph of a weighted graph where each pixel is a node and finds the threshold by minimizing the cut, which is essentially a cost function of separating two classes of nodes in the graph. So here are some results from some methods we discussed and some we didn't list but implemented as well. So here's Otsu's method, class variance difference, Tao's graph cut method. Guo used the standard Shannon entropy. It was pretty faithful to his original definition. Xiao, which used the gray level spatial correlation. Ramesh, which was another histogram method, and it would minimize the sum of variance between the two classes. And Kittler's clustering method. And we the back one. We can see that some of them did not perform quite well. Like the graph cut method was a little too restrictive, and others, like Kittler's method, was a little too permissive. You see it picked up some, that's from the shadow. It cast a shadow, so there would be a greater difference between that region and the calculated background. And so that could be corrected either by a more restrictive threshold or more intelligent background subtraction. But we weren't really trying to focus on what method of background subtraction, so we just took one that had good, strong results in the past and used that. But we can see that some of them got accurate results. And in another picture, there we go. This fish is turned at an angle towards the light, and it's casting a much stronger shadow, which is picked up as a false positive object in the foreground. And you can see the graph cut algorithm, being a little more restrictive, actually avoided that problem. So that was a benefit there. And probably the most ideal case we had was a nice broadside view of the fish with relatively high contrast to the background. But there were some problems. You can see where the tail kind of blends with the bush in the background was kind of lost on some of the algorithms. But some of the more permissive ones picked them up. And you'll notice that on occasion you get extra data around the fish. So we took that and said, we have some pretty good results here. What can we do to, remove this extra fat, if you will, the halo around the fish? So we used a method to find those edges in the binarized image. Everything outside the fish would be black, everything inside would be white. We would find those edges, and we would take a band around those edges and re-threshold them with a less fuzzy filter. Because part of the pre-processing step to remove noise was to filter the entire image. Because with the changing illumination of the water, excuse me, there would be a lot of noise in the background subtraction, so we had to use a filter so it wouldn't pick up too many false positives. So taking the band and using a less fuzzy filter to remove noise, we're able to sharpen it a little bit. You can see it picked up that fin a little better and even expanded this one a little better. So it fixed where it was too wide and where it was too thin in some cases. So we think we improved a little bit with that. And another improvement we added to the graph cut method in particular was an efficiency, because their method would use as many exponential multiplications as there were edges, but we factored that out and only did it as half of the many gray levels in the matrix. So that was basically our final results for thresholding, and these would be used for feature extraction and feature classification. To talk to you about that is Brent.
Thanks, Joe. First thing, the first step we did for classification, there's a process known as WARP, which stands for the Warp Accurate Retrieval phase. I'm not really sure who came up with it, not really creative, but the original paper was done on images of fish out of water, like just laying on a flat background, and they took the edges. To do this, it's a discrete Fourier transform. That's the type of Fourier descriptor algorithm that we use. The main benefit of this, you can retain more information with fewer points, which is really nice because your original set of Fourier descriptors is every pixel on the edge of the fish. So you're looking at around 500 to 600 pixels. That can take a long time to compute. This is the normalized DFT formula, where R is your R is your magnitude and theta is your phase value. And when you perform DFT on Fourier descriptors, the phase and magnitude values are just, it's kind of ways of, it's information that says, oh, this point is here in relation to the others. Just some basics. In order to determine our subset from all these 500-600 points, we used the energy to reduce it, which was just we took the R values, squared them, and then we summed it up and we did a ratio. So let's say we wanted to do 64 points, see how much information is really retained. We just did a ratio of the energy from 64 points to to the entire subset. And we found for these experiments that if we used 128 points, that gave us about 0.99 of the energy. So we were pretty pleased with that, and it wasn't very taxing on the computation. So then one of the downsides with discrete Fourier transform is that you don't retain your phase and magnitude information. Normally what will happen is you just, when you get your DFT values for each point, you just take the absolute value, and that's what you use to compute. So if you have two images, you don't really know anything other than any important information about it other than this is what it looks like. So in order to keep the phase and magnitude, you have to modify it. To modify the magnitude, we just, it's a pretty standard modification. You just take each magnitude and divide it by the first magnitude. And it's pretty simple. And then for the phase, you see, this is actually two equations put together. The first part of it, theta sub m minus theta sub -1 plus theta sub 1 over 2, is actually deals with your your starting point. So by modifying it, okay, this point on the fish edge is where I'm actually starting my where I'm actually starting and going around the fish to do calculations. The second part of it is scaling, because obviously one of the benefits of warp is that if you have two of the same image but they're completely different sizes, you can actually tell if they're the same species or close enough to the same species or not. And then, as you see also, we set the DC coefficient, which is when you order the DFT values by frequency, they go from, like, if you have 64 points, they would go from -32 to 31. And so the value that would be, if you think of an array like it's base 0, we set that equal to 0 because that will translate the entire image to the origin, so that way you don't have to worry about, images being in unusual places or anything like that. So then once we've computed those normalized DFT values, we then use a distance measure that's called dynamic time warping. One of the benefits of this is that it's not a regular distance measure like if you think of Euclidean distance, because if we did Euclidean distance on two different fish images, because they could be slightly different even if they're the same species, you're going to run into the problem of, oh well, it's comparing this one point to another that's just off, and that could give you a really big difference in your distance measure and throw in error. So dynamic time warping goes with the idea that you may not have a direct comparison. So what it'll actually do is it'll calculate the distance between one point and every other point and find that minimum value, because it goes, oh, okay, these are the two closest in reality. They have to correlate to each other, rather than just blindly computing distance between two points that should be the minimum and it actually isn't. And one of the downsides with this, though, it's a recursive function, so it's a very computational heavy function. Just some basic tests on two sets of points. When there were 8 points in each set, it ran in about 4 or 5 seconds. At 9 points, it ran in 24 seconds. And when we bumped it up to 10 points, it took about 8.5 minutes. So you can't classify with that few points, so it's not worth it. Thankfully, there's a method called the Sekoe-Chiba band. This was actually developed back in the 70s to use in voice recognition algorithms to reduce time. And what it does is, if you think of a matrix, and with each cell in that matrix is a distance value between 2 points, the Sekoe-Chiba band, it goes with the idea that if you go along that diagonal and you have a certain band, like you set the bandwidth manually, you're going to say all the minimum distances you need to calculate dynamic time warping are going to be within that band. Now there may be an outlier or two that are outside of that, but for the most part, you're going to pretty much get every minimum distance you need. So then all you really have to do is sum up along that diagonal of the matrix to calculate the distance between those two images, which is really nice. I mean, it cuts computation time down to milliseconds, I would say, between two images. So for the warp results, when we did just a straight Euclidean distance comparison, not using warp, it was about a 21.2% recognition rate. And that was even with a threshold, like we said, you know, if the distance is under 5, consider them the same species, you know, just because you account for that fact that they may not be perfectly 0. Then what we did is we did a warp direct image comparison where we said, all right, we have an image in our probe set and we have an image in our gallery set. Is the probe the same species as the gallery, just with straight dynamic time warping?
One quick question, how do you define the recognition rate? How many?
It's just how many are correctly identified as of the same species or not. So it's like,
how many examples do you provide?
that's actually, I'm going to get to that, that's in the problems. The direct image comparison was 53.2%, so there was a significant improvement, but still 53% is not a great number for automatic recognition, especially because there were a lot of misclassifications in the sense of it would say an image is not of the same species when it is of the same species, and that's a bad error, you know, or it's a worse error than saying an image that isn't of the same species actually is in biometrics. So what we then worked on was we did what I just kind of call it the average distance comparison. And what I did is I had a set of images, you know, I want to say we ran it with, there was about 27 images, all of different species, or there were like 4 or 5 different species in it. And we went through each image in that list and compared it to a set of images that were all of the same species. And based on that, and then we would average the distance values it got, and we would say if that average is less than 5, they're of the same species. In doing that, we got an 86.4% recognition rate. So as it stands with warp, it looks better if you have essentially a database of fish and you've got different species in it, and you have a fish image and you're like, you want to know what species it's in, it's much more effective to then say, okay, let's run through this species of fish, see what the distance is, and see if it's close enough. And that way, you know, it works best when you already have a database. If you're just trying to sort fish into different species, warp's not going to be particularly effective for that. But then going on to some of the problems, the biggest one kind of in the end was that we didn't have enough images. Out of a set of 1,800 images, there were only 54 viable images to perform testing on. Part of that is background substitution. You know, there's just no great way to get a perfect silhouette of the fish. You know, even the best ones, there were still, like, you may miss a chunk of the eye or something like that, which is a problem. Also, if the fish are oriented at unusual angles, you know, turning into or out of the camera, that affects the shape. So it makes it harder for warp to work because, you know, they may not have a profile of that shape in the database, which runs an issue. And the other issue is that the fish species are too similar in shape. You could run into issues just because we are using the shape we are using the shape of the image and not we're not using texture or anything like that. But warp's definitely something that if you get a bigger data set, get some more conclusive information out of it. And then for Gabor filters, what Dr. Holompides had mentioned is that there's one species of fish, the Emorio, that has a vertical stripe on the tail that's of a much lighter color. And so he was curious about trying to highlight that stripe to classify the Emorio, like whether the fish was an Emorio or not. And so what we did with that is we used Gabor filters. We ran a horizontal and vertical Gabor filter over the input image, and then we took a ratio between those two outputs, and that gives us a very distinct texture variation. So that, like, the essentially lighter areas show up kind of if you think of a wave, like they show up as a big wave on the image. And so after that, we thresholded the image into a binary image so that the lighter areas became pure white, darker areas just went straight black. And then we automatically searched for the tail. You know, I think we used, if there was a band with a width of between 5 and 15 pixels and a length of above 20 pixels, we said, oh, this is an Emorio fish. And this is an example. The fish on the left, that's not Emorio. The fish on the right is an Emorio. You can see these are the ratio of the Gabor filters. You can see that very distinct edge on the tail. And so basically, the recognition rate ended up, it was 90.7% that it would say this is an Emorio or isn't an Emorio correctly, which is very good. Pleased with that. This is common. Well, the one downside is the problems that come up are if the camera has a light on it, like a distinct light, and that hits the fish, you'll get an unnatural band of light on the fish. So that gives you a misclassification, as does if you can't see the tail. You know, obviously you can't see the distinct stripe. But those were the only two real misclassifications. As long as we could see the tail, we properly classified it. So now Colin's going to talk about neural networks and classification.
So I was interested in classifying using neural networks, and so I implemented 3 basic architectures from literature. The first one was convolutional neural networks, restricted Boltzmann machines, and deep belief networks. So the convolutional network is actually really nice for image data. It preserves spatial information that's in the original input image, as well as using weight sharing so that it's efficient for large image dimensions. So you have an input image as your input to the network, and then in your convolutional layers you have several feature maps, and each neuron in a feature map corresponds to a particular location in the input image, and its inputs are a 5x5 region around that pixel location in the input image. And that 5x5 weight matrix is actually shared among all neurons in that convolutional layer. So updating the convolutional layer is as simple as running a convolution on the input image, which makes it very efficient. And then the subsampling layers merely downsample that image, and you alternate convolution and subsampling layers. And then for your final output layer, it's just standard neurons. Restricted Boltzmann machines are slightly different. Rather than the normal neural network feed-forward sort of design, it has 2 layers, a visible and a hidden layer, and you would apply your input to the visible layer, and then sample your hidden layer, and then resample the visible layer, and that would be the network output. And what you train it to do is to actually reproduce the images that you present to it, or the patterns you present to it, and it learns a model of your data space. So we were interested in using this as perhaps a pre-processing step to recover missing data due to poor segmentations. And I also implemented a deep belief network, which is really just a stack of restricted Boltzmann machines. So if you imagine the hidden layer encodes features of the visible layer, your next layer would encode features of those features, and it gives more powerful reproduction abilities for your input data. So the test I used binary fish images that were extracted from the video. So we're only using the shape data, and they were automatically normalized for rotation and size. The images were selected by hand, as Brian mentioned, because the quality varied so much. So we used 17 training images and 42 testing, but we accounted for different horizontal orientations, and so we also trained on their mirror images. And the classification goal was to identify Emorio versus other fish. So we did 2 experiments, one using only the convolutional neural network with the raw image data as the input, and the second used the deep belief network as a pre-processing step. And so these are the network parameters. Convolutional network trained fairly quickly. It took 5 to 10 minutes to train on the data set. The deep belief network took much longer, several hours. And so what we did was we used a pre-processing step to reduce the amount of data necessary to train and use the deep belief network, where if a pixel was either always 1 or always 0 in our testing images, we assumed that was its value and skipped presenting it to the deep belief network and just set that value when presenting it to the convolutional network. So using only the convolutional network, we misclassify 6 images, giving us a 93% accuracy. And these are the 6 images misclassified. One of them you can see has a severe artifact from the segmentation. When we pre-process these images with the deep belief network, we only misclassify those top 2. The rest of the data seems to be recovered. Yes?
Still one quick question. When you say misclassify, how many classes and what are these correctly classified fish species?
Because
by looking at these 6 images, I cannot really see what type of fish it is.
Right, it classifies as Emorio or other. With these images, I actually could not tell you for certain. It's easier to see with the original pixel data. You can see that stripe on the tail on most of them. I believe the bottom one is probably definitely not Emorio, and the middle one I think is Emorio turning away from the camera. But those...
I'm thinking by presenting this processed fish image to even a taxonomist, like an expert, do you believe that he or she can correctly classify it's an Emorio or not?
I think it's difficult, but the Emorio definitely has a distinct shape that's visible even in the outline. And so the deep belief network seemed to definitely improve results. I did one other test, which was just applying that pixel pre-processing and then running the convolutional network just to make sure that normalization wasn't the cause of the better results. That actually significantly decreased results. So I feel confident in saying that the deep belief network, at least on this data set, improves the results.
And these are on testing data. So this,
yes, this is testing data that the network didn't see.
Do you know like the classification accuracy on the training data?
The training data, I believe it classified perfectly. So now we have some conclusions.
So briefly, yes.
How big was your thing? You were testing how many images?
It was one more. It was 84 testing images, but it was really 42 original images and also their flipped versions. It was about half Emorio, half other. I don't remember the exact split.
And does it same test data for all the like,
Right.
Okay, well, briefly in conclusion, we in the end had a good comparison of different thresholding algorithms that we implemented from scratch from the literature. And we also improved one method and developed a process to improve the data from the actual algorithms.
We also were able to test the validity of warp on non-ideal images, so we could extend a previously published paper by a different group. We also identified Emorio fish based on just the existence of the tail stripe.
And the convolutional network did perform as well as hoped on this image data. It definitely seems to be an appropriate architecture. And at least on this initial test, the deep belief network helped classification.
I guess for our future work, we would like a way to use each of the thresholding methods and then have a way to pick the best one to send to the further processes. And for that, we would need some kind of criterion that's not qualitative, that we say this one looks better. It would be nice to have some kind of empirical test to choose our threshold method.
Also, the biggest thing with the warp and Gabor filter is just to get more data, because right now the results are good, but they're still elusive.
Yeah, a larger data set will help with the neural network test as well, especially improving confidence that the deep leaf network is a useful pre-processing tool. Different network training parameters could also be investigated. There wasn't really time to get too much into that during this research.
Any other questions?
Another one. When you say you have one type of fish and then another class is not that type of fish, do you have some representative examples for the other class? Because to me, if you have two different fish species, it's easier to do the classification. But if you say the other class is not this type of fish, what type of examples are you going to provide?
Those were drawn from the video stream we had. I believe it was mostly one or two other types of fish for the majority of the images.
Essentially, how he did his neural network, I did my Gabor filter, was, I want to say there appeared to be 4 or 5 different species of fish, including Emorio. And what we did for those experiments was we knew which ones were Emorio, and that was one class. And then we essentially had a second class that was not Emorio. We didn't, because I didn't know of any distinct features in those images that Gabor filters would work, and because, Colin was just trying to identify the Emorio with his things, we only separated into 2 classes. It was either, yes, this is Emorio, or it's something else, but we don't care what else it is. We weren't worried about that, because the distinctness in their shape wouldn't, we were okay with that, because all the shapes were that distinct.
And what's the size of the examples for not Emorio?
I mean, it depends on, I think Colin said he had about a 50-50 split, so he had 21, 21. Mine it varied. I think Emorio, I want to say I had 16, and then I had 6 of another species, 2 of another, and I want to say about 20 of another, but I'm not sure about the exact numbers.
I think this might be a bit out of the scope, but do you consider possibly engage some existing classification schemes just directly to the training sample and compare with your convolutional neural network or some other techniques? Because there are many classification toolboxes, including feature discriminant analysis or some support vector machine or among many others. Do you think that, for instance, convolutional neural network has a certain competitive edge compared with other methods?
I think on raw image data, the convolutional network outperforms other architectures, at least in the literature. But for example, for classifying other specific feature vectors, I think further investigation of different architectures would be useful.
No. There were only 4 or 5 different species. What I was saying was half of them, like in Colin's, half were Emorio, the other half were just a combination of the other species.
How many did you use to train your
Species or images?
other species which are not Emorio?
I couldn't actually tell you because my discriminating ability was only Emorio versus not Emorio. I think based on their shape, there were 2 or 3 different species.
So for the background subtraction, yes, you said you're going to make a more intelligent thresholding, selection. Well,
And you have bunch of different techniques. So is there a way to make a hybrid of it, where it takes the best abilities of each of the algorithms?
well, background subtraction has to happen before the thresholding, because if you tried to threshold the image on the left, if you imagine the fish are in the image on the left,
Yeah.
you would get nonsense. I mean, the light areas of the fish would be white, the dark areas of the fish would be dark. What you need to threshold is the image on the right, which shows non-background versus background intensity differences.
My terminology is shit, but pretty much the idea is I'm taking this image on the left-hand side and comparing it to the right-hand side and kind of getting rid of it, basically.
Well, yeah, that's exactly what you're trying to do. But
And
it's the fact that it's the environment has a lot of illumination noise.
Yeah.
Like the light's changing, so the median's going to be distorted by various light changes in the water. Or I don't know if you can see it, but there's like underwater weeds or whatever moving around, so that'll skew the median. And you could the version we uses a buffer, so it doesn't take the entire sequence into consideration. So it's a little smarter because it takes a smaller range. But yeah, that's different things that have to be adjusted. And I mean, that's just the method that was suggested before we even started. So we didn't do a whole lot of.
Okay, so the other different techniques, whatever that is, the different like goo and these guys here.
Yeah.
So is there a way to make like a hybrid of it, in which you can like take the best of each of them and sort of put it together?
That's what we would like to do, yeah. And we tried using comparisons, like compare this binarization to this binarization.
Mm-hmm.
But that's essentially what we're doing with the edge thinning.
Okay.
You know? So we say maybe, oh, there's this much error, so we'll segment this edge, this band, and then we shrink the band. And so the edge thinning runs over a whole different size bands, essentially eating away that extra
Yeah.
pixels.
Because could you almost like do them all and then sort of compare them and say most probable fish is this?
You probably could, and that's what we would, you know,
Yeah.
that's what I meant in the future work. But
That was sort of, I was kind of thinking.
yeah, that's exactly what, yeah. What we're
From this experience that you had in the background subtraction, do you think that could be possible? Because all these algorithms are computational demand.
Hmm.
Do you think that it's possible to reduce the computational process of all these? Do you think that you can come up with a scheme, or do you have in mind something like that?
Like do the subtraction and thresholding in one fell
Yeah,
swoop?
or like, because I guess for these ones you didn't use the 100. Like, how many frames did you use for?
Well, there were 230.
200, yeah, you
There were
used
230,
200,
but one was from a left lens and one was
Yeah.
from a right
Yeah.
lens. So you couldn't combine them.
Yeah, 100 frames. Yes.
Yeah.
But do you think like it could be possible, for example, say like only use 3 frames or 2 frames?
Uh-huh.
Do you think? Like just as a comment, can you?
You could, but you might need some pre-existing knowledge. Like you might need a background already, because it'd be very difficult to compute a background from that. That's the problem. That's why you need a lot of images, because you don't know what is not there to begin with. You know, if you only had 3 frames and a fish is here, then it moves like an inch, and it moves another inch. The background is going to be a really long fish there. You know, and so when you subtract it.
Dr. Harlan Peters and I, we took the existing background substitution and tried to reduce the number of frames we needed, and there was a ridiculous amount of noise. So if it was going to happen, like if we were going to do that, there would have to be a fundamental change to the background substitution algorithm itself. As it's currently written, you need a significant number of frames, because that's actually one of the reasons we didn't have enough data. We had data in folders separated by species, but only eMorio had enough images to do a proper background substitution on, and that was at 100. Like, some of them I want to say were at about 20 images, and we reduced, we tried to use only like 5 or so at a time to do background substitution, but it didn't give you a good image of the fish. So I guess the answer is it's probably possible, but it's, not with the current algorithm. You would need a big change.
The running mean would have to be changed.
Yeah.
Another for the neural network thing. So that pretty much just classifies it based on like a shape or an outline in a sense.
Right, yeah, it has that binary image where white is the fish and black is background. And it classifies based on those pixel values, where white is 1 and black is 0.
So it classifies it based off of the Fourier descriptors or outlined in any fashion?
For the neural networks, it just turns that image into a vector of 1s and 0s, and that's the input to the network.
Okay, so it pretty much says, okay, so you sort of like distort the image, and I'm trying to figure out on actually how it works. So it takes this, and it says it has this specific dimensionality to it, so it's more likely this, in a sense. I don't know.
Something like that, yeah.
Okay.